Right now, at the edge of our observational limits, telescopes are capturing light from explosive cosmic collisions that completely defy our standard models of physics. We are looking at the aftermath of dead stars tearing each other apart, and the spectral data arriving at our detectors contains signatures of elements that simply do not belong on the periodic table as we know it. For decades, we have understood how the universe forges the building blocks of reality. Hydrogen and helium were born in the primordial fires of the early universe. Carbon, oxygen, and iron are forged in the crushing cores of living stars. The heaviest elements like gold, platinum, and uranium are violently created when massive stars die or when ultra-dense stellar corpses collide in the dark. But recently, a careful examination of the fading light from these cataclysmic mergers has revealed a profound anomaly. There is a strange, persistent glow in the infrared spectrum that decays at the wrong rate. The opacity of the radioactive debris is far higher than our computational models can account for. The data suggests that these stellar collisions are not just creating standard heavy metals. They might be leaking a deeply exotic, purely theoretical substance into the interstellar medium, a substance that has the power to fundamentally rewrite the rules of chemistry and restructure the periodic table itself. To understand the sheer magnitude of this data and why it challenges the very foundation of atomic physics, we have to look past the surface of the stars and dive into the subatomic architecture of the universe. If you enjoy exploring the deep mysteries of the cosmos and unraveling the fundamental nature of reality with me, take a moment to subscribe so we can continue investigating these scientific anomalies together. The sheer scale of what astronomical observatories are currently recording demands that we question everything we thought we knew about matter. The source of this profound mystery lies within the crushing interior of a neutron star. When a massive star reaches the end of its life, having exhausted all its nuclear fuel, it can no longer generate the outward radiation pressure required to fight the relentless inward pull of its own gravity. The core collapses in a fraction of a second. The outer layers of the star are blown away in a spectacular supernova explosion, but the core is crushed violently inward. If the collapsing core has a mass between 1.4 and roughly 2.1 times the mass of our Sun, the gravitational force is so extreme that it overwhelms the fundamental forces that keep atoms intact. In a normal atom, the nucleus sits at the center, surrounded by a vast cloud of orbiting electrons. The atom is mostly empty space, but during the collapse of a massive stellar core, gravity crushes that empty space out of existence. Electrons are violently forced into the atomic nuclei, where they collide with protons. Through the process of the weak nuclear interaction, these electrons and protons fuse together, transforming into neutrons and releasing ghostly particles called neutrinos that stream away into the void. What remains is a sphere just 20 kilometers across, yet containing more mass than our entire solar system. This is the neutron star, a city-sized atomic nucleus suspended in the vacuum of space. The conditions inside this stellar corpse are so extreme that they defy standard human intuition. A single teaspoon of neutron star material brought to the surface of the Earth would weigh 1 billion tons. The outer crust of the star is a rigid lattice of heavy atomic nuclei, bathed in a sea of highly energetic electrons. But as we move deeper into the star, the pressure increases exponentially. We reach a threshold known as the neutron drip line. At this unimaginable depth, atomic nuclei are so oversaturated with neutrons that the neutrons begin to literally leak out, forming a frictionless superfluid that permeates the inner layers of the star. This is where the standard model of physics begins to struggle. Deep within the inner core of the neutron star, the pressure is so immense that even neutrons themselves cannot survive intact. To understand what happens next, we have to look at the internal anatomy of a neutron. Neutrons are not fundamental particles. They are composed of smaller, elementary particles called quarks. Specifically, a standard neutron is made of one up quark and two down quarks. These quarks are bound together by the strong nuclear force, which is mediated by the exchange of massless particles called gluons. Under normal conditions, quarks are strictly confined. You can never find a solitary quark in nature. The strong force is so powerful that if you try to pull two quarks apart, the energy required to separate them spontaneously creates new pairs of quarks, snapping them back into bound states. This principle is known as color confinement, but the inner core of a neutron star is not a normal condition. The density at the center of the star reaches levels of hundreds of millions of metric tons per cubic centimeter. The neutrons are packed so tightly together that their boundaries begin to overlap. When this happens, a phenomenon known as asymptotic freedom takes over. At extremely high energies and unimaginably short distances, the strong nuclear force between quarks paradoxically grows weaker. The overlapping neutrons dissolve, losing their individual identities. The quarks are liberated from their microscopic prisons, creating an ultra-dense, free-flowing state of matter known as a quark-gluon plasma. We are no longer dealing with atoms. We are no longer dealing with protons or neutrons. We are looking at a macroscopic ocean of pure, deconfined quark matter. And this is where the mystery introduced by the recent observational data begins to take a fascinating and terrifying shape. The laws of quantum mechanics dictate how these free quarks must behave, specifically governed by the Pauli exclusion principle. This principle states that no two identical fermions, like quarks, can occupy the exact same quantum energy state simultaneously. You can think of quantum energy states like the rungs of a ladder. As more and more up and down quarks are forced into the core of the star, they quickly fill up all the available low-energy rungs. The newly added quarks have no choice but to occupy increasingly higher and higher energy states. In physics, systems always seek their lowest possible energy state to achieve stability. A system with quarks pushed to extraordinarily high energy levels is inherently unstable. Nature provides a loophole, a mechanism to relieve this enormous quantum pressure. Quarks come in different flavors. While normal matter is made entirely of up and down quarks, there are heavier flavors including the strange quark. The strange quark is significantly more massive than the up and down quarks, and under normal circumstances on Earth, it decays away in a fraction of a second. But inside the extreme pressure cooker of a neutron star core, the rules change. Because the strange quarks are entirely different particles, they have their own empty quantum energy ladder. Instead of forcing an up or down quark onto a dangerously high energy rung of their crowded ladders, the extreme environment allows some of those high-energy down quarks to spontaneously transform into strange quarks via the weak interaction. They change flavor, emitting energy, and dropping down to the lowest, empty rungs of the strange quark ladder. The entire energy state of the core lowers, locking the system into a deeply stable configuration. This resulting mixture of roughly equal numbers of up, down, and strange quarks is known as strange matter. And this is where the theoretical physics community faces a deeply profound and unsettling hypothesis. For decades, theoretical physicists have proposed that strange matter might not just be a peculiar phase of matter existing deep inside dead stars. It is mathematically plausible that strange matter is the absolute true ground state of all matter in the universe. Standard matter, the protons and neutrons making up your body, the Earth, and the Sun, might actually be existing in a false vacuum, a metastable state. It is stable only because the energy barrier required to convert standard matter into strange matter is incredibly high. But once that barrier is broken, as it is in the core of a neutron star, the resulting strange matter is virtually indestructible. It is the most perfectly stable substance in the cosmos. This stability introduces a frightening property. Strange matter is theorized to be highly infectious because it represents the ultimate lowest energy state in any normal atomic nucleus that comes into physical contact with a droplet of strange matter would instantly be converted into strange matter itself. The normal quarks would be dragged down the quantum energy ladder, transforming their flavors, releasing a massive amount of heat and radiation, and becoming permanently bound to the strange droplet. If this theoretical framework holds true, why hasn't the strange matter inside a neutron star eaten the entire star? Why hasn't it consumed the universe? The answer lies in the intense gravitational constraints and the electrical properties of the star. The strange quark core is suspended at the very center of the star, held in place by immense pressure. Furthermore, strange matter droplets, often called strangelets, carry a slight positive electrical charge. Normal atomic nuclei are also positively charged, because like charges repel, there is a natural Coulomb barrier, an electrical force field that prevents normal atomic matter in the outer layers of the star from falling directly into the strange matter core. The star reaches a delicate, terrifying equilibrium. The strange matter is safely quarantined behind gravity and electromagnetic repulsion, locked away forever. Or so we thought. The precise anomaly in the recent telescopic data suggests that this quarantine does not last forever. The universe has a mechanism for breaking these stellar containment vessels open. When two massive stars are born together in a binary system, they can both eventually explode as supernovae, leaving behind two neutron stars orbiting a common center of mass. Over millions of years, as these ultra-dense corpses relentlessly circle one another, they stir the very fabric of space-time, radiating energy away in the form of gravitational waves. As energy bleeds out of the system, their orbit shrinks. They spiral closer and closer together, their velocities increasing to a significant fraction of the speed of light. In the final few seconds before they collide, the gravitational forces they exert on each other become absolutely unimaginable. The tidal forces stretch and distort the solid crusts of the stars. The gravity of one star pulls violently on the near side of its companion, while the far side lags behind. The immense structural integrity of the neutron star crust, billions of times stronger than steel, finally fails. The crust shatters, fracturing continents of degenerate matter and triggering starquakes that rip through the stellar interior. When the two stars finally smash together in a cataclysmic event known as a kilonova, the violence of the impact sends shockwaves rippling through the liquid ocean of the interior, all the way down to the strange matter core. The collision splashes stellar material outward at immense velocities, while the vast majority of the combined mass collapses rapidly into a black hole. A significant fraction of the outer layers, and potentially fragments of the deep interior, are violently ejected into the interstellar void. This is the exact moment we must examine closely to understand the anomalous spectral data. In the chaotic, expanding cloud of radioactive debris surrounding the newly formed black hole, the conditions are perfect for an event known as the rapid neutron capture process. This process is responsible for creating the heaviest known elements in the universe. The ejected material is a cooling soup of completely free neutrons and highly excited atomic nuclei. Because neutrons have no electrical charge, they are not repelled by the positively charged atomic nuclei. The nuclei capture free neutrons at an astonishingly fast rate, far faster than the radioactive decay process can break them apart. They bloat into massive, unstable, superheavy isotopes, which then undergo beta decay, transforming some of those newly captured neutrons into protons, thereby inching their way up the periodic table to become elements like gold, platinum, and uranium. But the data tells us that standard rapid neutron capture cannot fully explain the persistent, highly opaque infrared glow of the collision aftermath. The light curve we observe requires the presence of seed materials far more massive than anything standard physics predicts. This brings us back to the shattered core of the neutron stars. During the violent tearing of the merger, it is physically possible that the violent shockwaves and tidal disruptions forcefully dredge up small fragments of the strange matter core, ejecting microscopic droplets of pure strange matter, the highly infectious strangelets, out into the expanding debris cloud. These strangelets would act as incredibly massive, perfectly stable seeds in the rapid neutron capture process. Unlike standard atomic nuclei, which become highly unstable and split apart via nuclear fission when they get too large, strangelets do not suffer from the same instability. The repulsive electrical force between protons usually tears heavy nuclei apart. But in a strangelet, the addition of the strange quarks mitigates this repulsion, locking the system together in a deep energy well. As these strangelets fly through the neutron-rich debris of the kilonova, they effortlessly sweep up normal neutrons and protons. When a standard nucleus absorbs standard matter, it just makes a heavier standard element. But when a strangelet absorbs standard matter, the infectious nature of the strange quarks takes over. The newly captured protons and neutrons are instantly dissolved, their constituent up and down quarks forced into the strange matter state. The strangelet simply grows larger and more massive, releasing immense amounts of binding energy in the form of gamma radiation. As the expanding debris cloud cools, these growing strangelets capture standard electrons to balance their positive electrical charge. The result is an entirely new class of atomic structure, a superheavy element with a core made not of individual protons and neutrons, but of a single, continuous, deconfined strange matter droplet surrounded by a massive electron cloud. This theoretical mechanism fundamentally alters our understanding of the periodic table of elements. Currently, the periodic table ends at element 118, oganesson, an artificial element synthesized in particle accelerators that decays in a fraction of a millisecond. Standard nuclear physics predicts an island of stability further up the table, perhaps around element 120 or element 164, where magic numbers of protons and neutrons might arrange themselves into perfectly spherical, stable configurations, extending the life of the element to minutes or days. However, the introduction of strange matter seeds rewrites the rules of nuclear binding energy. The strange periodic table would not end at element 118. It might not end at all. Strange matter cores could theoretically support atomic numbers of several hundred or even thousands. These would be microscopic specks of unimaginable density, behaving chemically like elements we have never seen. They would have massive, sprawling electron orbital configurations, leading to highly complex chemical bonds and physical properties that we cannot accurately model with current quantum chemistry equations. If strangelets are indeed acting as seeds for the rapid neutron capture process during stellar mergers, it explains the deep anomalies in the observational data. The extremely complex electron orbitals of these superheavy strange atoms would interact with light in highly unusual ways. The F-shell and G-shell electrons in these massive atoms would act as an incredibly dense thicket, absorbing virtually all visible and ultraviolet light, while allowing highly red, shifted, persistent infrared radiation to slowly leak out. This perfectly matches the exceptionally high opacity and the strange, long-lasting infrared glow we detect from kilonova light curves. The data is practically screaming that something heavier than standard actinides is dominating the radioactive decay within the debris field. But as we peel back this layer of understanding, a new, far more unsettling question emerges. If these cosmic collisions are actively forging stable, super-heavy strange elements, where are they going? The expanding debris cloud of a kilonova doesn't just disappear. It spreads out across the galaxy, traveling across thousands of light years over millions of years, eventually mixing with the interstellar medium, the vast clouds of gas and dust that eventually collapse to form new star systems, new planets, and potentially new life. This means that fragments of the strange periodic table could be drifting through our very own solar system right now. In fact, for decades, researchers analyzing high-energy cosmic rays striking the upper atmosphere of the Earth have recorded incredibly rare, highly anomalous events. Occasionally, particle detectors record impacts from cosmic rays carrying a mass-to-charge ratio that defies standard nuclear physics. These particles appear to be incredibly heavy, yet they carry a disproportionately small electrical charge. For a long time, these events were dismissed as instrument errors or deeply misunderstood standard interactions. But viewed through the lens of the strange matter hypothesis, these anomalous cosmic rays look exactly like the theoretical signature of strangelets traversing the galaxy. If you are finding this deep dive into the hidden mechanisms of the universe valuable, and you want to support more rigorous, data-driven scientific analysis, please leave a like on this video. It truly helps push these complex scientific topics out to a wider audience and allows us to continue making content like this. The implications of discovering strange matter interacting with normal matter on Earth are staggering. We established earlier that strange matter is infectious, converting normal matter upon contact. But the microscopic strangelets potentially forged in the aftermath of neutron star collisions are moving at immense relativistic velocities. When they strike the Earth, they do not have time to settle and consume normal matter. They smash into the molecules of the upper atmosphere, instantly shattering into a shower of secondary subatomic particles, dissipating their energy harmlessly in a cascade of pions, muons, and neutrinos. However, what if a strangelet was significantly slowed down? What if a massive strange atom, forged in a distant kilonova, became trapped within an ancient asteroid, shielded from high-speed collisions, eventually falling to the surface of a planet as a meteorite? Theoretical models suggest that a strangelet resting on the surface of the Earth would not instantly consume the planet. The microscopic size of the strangelet means its positive electrical charge would still generate a Coulomb barrier, pushing the positively charged nuclei of terrestrial atoms away, preventing the deadly physical contact required for conversion. The strange atom would sit there, immensely heavy, incredibly dense, but inert. Yet this theoretical safety net relies heavily on our incomplete understanding of quantum chromodynamics. If the precise charge of the strangelet fluctuates, or if extreme environmental pressures somehow overcome the Coulomb barrier, the strange matter contagion could theoretically ignite. This forces us to question the exact composition of the deepest, oldest rocks on Earth and the strange isotopic anomalies occasionally found in meteorites. Could the microscopic seeds of dead stars be hiding in plain sight, masquerading as exceptionally dense isotopes of standard elements? Our ability to answer these questions is rapidly accelerating. Next-generation gravitational wave observatories are being brought online, vastly increasing our sensitivity to the ripples in spacetime caused by stellar mergers. By analyzing the precise frequency of the gravitational waves during the final milliseconds of a neutron star collision, we can measure the tidal deformability of the dying stars. This measurement directly tells us the stiffness of the star, allowing us to accurately map the internal equation of state. If the star is extremely rigid, it is likely composed of standard neutrons. But if the star is remarkably compressible, squishy, and compact, it provides massive evidentiary support for a core composed of pure strange quark matter. Coupled with these gravitational measurements, space telescopes are peering deeper into the infrared spectrum of the resulting kilonova explosions. By securing high-resolution spectroscopic data of the expanding debris clouds, we can look for the specific absorption lines of superheavy elements far beyond the known periodic table. We are hunting for the unique spectral fingerprint of strange atoms, the precise wavelengths of light absorbed by the sprawling electron shells of strangelet cores. Every new collision we observe adds another piece to the puzzle. We are no longer simply charting the stars. We are actively observing the universe running ultra-high-energy particle physics experiments that we could never replicate on Earth. The data we are gathering right now is tearing down the traditional boundaries between astrophysics, nuclear physics, and quantum mechanics. The periodic table, the foundational map of chemistry that hangs in every classroom on Earth, might merely be the shallow end of the elemental spectrum, cataloging only the fragile, metastable matter that happens to exist far away from the crushing gravity of dead stars. The anomalous infrared light reaching our telescopes today is a direct message from the extreme frontier of physics. It hints at a universe far richer, far stranger, and far more complex than we ever imagined. A universe where the death of one star is not simply an end, but a violent forge, creating utterly alien forms of matter, scattering the seeds of a strange new chemistry out into the dark. The true nature of the elements that construct our reality remains one of the greatest unresolved mysteries of modern science. And as the data continues to pour in, we are steadily moving closer to an answer that could change our understanding of the physical world forever.